In this video, we're going to jump back a little bit and look at the geometry that might help us visualize these operations that we've been performing with vectors, the vector addition and the vector subtraction, even though we didn't formally define subtraction, and scalar multiplication. So let's actually start with addition and subtraction. So suppose we have two vectors u and v like this. So let's say here is u and here is v. And I'm having them start at the same initial point. And the word, so when two vectors have the same initial point, the vectors are said to be concurrent. And that word comes up a lot when you use vectors to analyze forces. So you might have come across that word in a course in maybe physics or static. You have this idea of concurrent forces. Well, that just basically means that they have the same initial point. So u and v have the same initial point. And we know a few operations now that we can perform with these two vectors. So we know algebraically how to add two vectors, right? And if we have the component form of u and v, all we have to do is add the corresponding components to get the components of u plus v. But then since I can sketch u and v, then it seems like I should be able to sketch u plus v relatively easily. And one thing that we can do is to create a parallelogram, right? So I'm going to create a parallelogram by essentially duplicating v and have that vector, the duplicate of vector v, have it start at the terminal point of view. So basically complete the parallelogram by doing this, right? So this is also v. And then of course, then I'm going to make the fourth side of my parallelogram by completing it with u, right? So again, these two vectors are equivalent. These two vectors are equivalent. These two are parallel. These two are parallel. So if I think of u plus v as either first moving along the vector u and then moving along the vector v, then it means u plus v would be the vector that starts at this point and ends at this point. So like this. So that would be the vector u plus v, right? And just by doing that, it again geometrically we see that this vector u plus v is equivalent to the vector v plus u. So if I instead of going along the vector u first, if I decided to go along the vector v first, and then I would go from my initial point here to this point, and then add u, then I would end up at the same point. So it's almost like geometrically we just proved the commutativity property of vector addition. That it doesn't matter if you add u plus v or v plus u, you are going to end up with the same result. So pretty cool, right? So that's the sum. What about the difference, right? What about the difference? Well, remember, we didn't formally define the difference, but we said, okay, if we have u minus v, the way we think about this is u plus negative v. Well, and then so again, now we just showed that the vector addition, at least we did it geometrically, it's like proof without words. We showed that vector addition is commutative. So I could take u plus v, I'm sorry, u plus negative v, or I could take negative v plus u. Well, what would negative v look like? Well, negative v would basically be if I remember what the negative does, it just makes the opposite of the vector, so to speak. So if v starts here and ends here, then negative v would go in the opposite direction. So I'll just do that dotted below, right? So like this. So this is the vector negative v. So if I start at this point and then go back to where v started, then I would just have moved along negative v. And then if I add u to that, so now I'm doing this operation, then I would go from this point to this point. So if I put it all together, it looks like u minus v, which is the same as negative v plus u. I can represent that vector on my same parallelogram. In fact, it would be the vector that starts here and ends here. So it's like the other diagonal. So the u plus v is one diagonal vector, and then the other one is u minus v. Now we know that subtraction is not commutative, so the order here is very important. So starting here and then going here, that is the vector u minus v, or if I wanted to write it as negative v plus u, right? So really nice little kind of geometric interpretation of the sum and the difference of two vectors. It's basically you use the two vectors, you make them concurrent, create a nice little parallelogram, and then you carefully define the diagonals, right? So that's the sum and difference. Well, what about the scalar multiplication? Well, scalar multiplication, we kind of have an idea. We've made use of it in certain algebraic problems before. Now we're just going to make the geometric interpretation a little bit more formal. So let's say we start with the vector. Here's my vector v. Right? Well, when I multiply v by a scalar, it does not change the direction in the sense that it is still going to point along in the same direction, right? But it might be a longer vector or a shorter vector. So scalar multiplication has the effect of either lengthening or shortening your vector as if your scalar is positive. If your scalar is negative, that's where, like we saw up here, where it will change the direction of the vector. So let's sketch a couple possibilities. So if I take, and then maybe what I'll do is I'll draw all the other ones dotted, right? So this vector here, which is longer, right? It's longer, it has a greater magnitude than my original vector v. This would be a vector formed by performing this operation. So the blue vector would be kv, and the only thing I know for sure, since the blue vector is longer than the white vector, then k would have to be greater than 1. And this causes the vector to be, sometimes you could say, like you said, you can lengthen the vector, or you could dilate the vector. You can stretch the vector, right? And it has to be positive because it's pointing in the exact same direction, right? And then, but that scalar would have to be greater than 1, which would create that lengthening effect. If I have a vector that's shorter than v, then it would, but pointing in the same direction, right? It would still be a scalar multiple of v, but now that scalar multiple would have to be a proper positive fraction. So it would have to be a number strictly between 0 and 1. So it could be like a third or 3/4 or a half, right? But we have our scalar multiplication. It's just that now our scalar, in order to produce the shortening effect, that scalar would have to be some number between 0 and 1, right? Now, what happens if you have negative scalars? Well, that's where the direction will change. Now, it could have two effects, right? You could change the direction and you could lengthen it. So I'll use that one also in blue. But now if I have it going this way, and these I'll do solid, right? So now definitely this vector, right, is in the opposite direction of my original vector v, and it's definitely longer. So in this case, this would still be a scalar multiple of v, but now the scalar would have to be less than -1. It would have to be negative to change the direction, and then it would have to be less than -1 in order to lengthen it. So your k in this case would have to be less than -1, right? And then we can do something similar for the red. So we could, again, change the direction and shorten the vector. So, something like this. So on this side, again, it would be kv, and now your constant would be less than 0, but greater than -1. So it would be like this, right? And that's pretty much all the as far as multiplying a vector by a non-zero scalar. Now, what would happen to create something like this, right? Well, if k is equal to 0, right, then you end up with the 0 vector, and the 0 vector has no direction and no magnitude. So I mean, I shouldn't really say that it's a point, but yeah, that's essentially what would happen. But I'll just indicate that this would be the 0 vector, and the 0 vector is either 0, 0 like this in 2 dimensions, or 0, 0, 0 in 3 dimensions, right? So that's how you can sort of visualize scalar multiplication. Just a couple more things before we wrap this video up. Now, the interesting thing about these scalar multiples is that you notice, essentially, if I take all possible scalars, right, all positive, all negative, and 0, what do I get? I actually get a line, because then it would extend indefinitely this way and indefinitely this way. And what happens is all of these, so for instance, you have all these possible vectors. Let me draw them now not along the same line, but kind of separated. So, here is v, and then here is the dotted kv in blue, and then here is the let me give myself a little bit more room, the solid kv this way, and then let's do the red. So then like that, and then let's say that. So all these vectors, notice if you extend each of them indefinitely, what you end up with are parallel lines, right? So vectors are said to be parallel if they are scalar multiples of each other, right? So two vectors, right, are said to be parallel if they are scalar multiples of each other. Of each other. That means like V is so V is parallel, and I'll use this symbol for parallel. So is parallel to U if and only if V is equal to some constant times U, where K can be, again, yeah, some real constant. So if one vector can be expressed as a scalar multiple of another vector, then those two vectors are said to be parallel. So it's a little bit different than, saying parallel lines have the same slope. We're not really talking about slope now, we're talking about direction, and that direction is defined by these vectors. And if it's simply, if again, they're either pointing in the exact same direction or in the exact opposite direction, we don't really care how long they are, just really the direction. So it's the direction that defines whether two vectors are parallel, not their magnitude, right? So there are just a couple geometric concepts that are related to our algebraic vector operations, and it's good to keep in mind because being able to do the algebra is important, but knowing how it corresponds to the geometry can help us, at least intuitively, understand some deeper concepts. And yeah, so let's keep going and get to those deeper concepts. So I'll see you in the next video.